All right. Hey, everybody. Let's go ahead and get started. My name's Brian Norman. I work for JetBrains on the Kotlin compiler, but I am here to talk to you about neither of those things. And instead, we're going to talk a little bit about Compose. So it was about a year ago. I was working on a presentation for Kotlin Conf, and I was doing the standard keynote things of copying and pasting code from IntelliJ with rich style, pasting it into Keynote, duplicating the slides a few dozen times, setting up Magic Move to get all the rendering and animation that I wanted all working. And it was just a really frustrating, non-dev friendly workflow. So I started to experiment with writing some of my slides in Compose, and it was going really well. I had like a little bit of a prototype. Um, and I was like, maybe this is something that we could do. Maybe this is something that would be very possible. Um, Hadi had other ideas, um, but sorry, Hadi, I did it anyways. I presented that year with Compose at KotlinConf, and in fact, I presented again this year um, at KotlinConf with Compose, and I'm presenting to you now with Compose. Of course, like why would we not? So in all of this, I've kind of created a small little framework called Storyboard, um, but it's actually not really that interesting. It's just a little DSL that kind of gives you some composable lambdas that you can do some slide content in, and it handles a little bit of transitions between slides, but it's not really that exciting. It's less complicated than Navigation 3. Like, this is very simple stuff. But what kind of has been interesting is this need to recreate almost everything that you would find natively in Keynote in Compose now. I don't get arrows, I don't get shapes that would come with Keynote, and I don't get Magic Move anymore. So, like, all of that has to get kind of recreated. Now, specifically, of course, we're going to be talking about Magic Text, because Magic Move is, like, a lot. So let's talk about what I've kind of done. So if we imagine some kind of like before and after code that we want to animate, we as humans can look at this and go, okay, you changed Kotlin conf to droidcon. Simple enough, but how do we actually get Compose to do something with that? My first idea was, what if we did something really basic? What if we just did like a line ending change of some kind? We could find the common prefix of each line and then go line by line and just kind of remove characters and then add characters, right? You could create kind of a list of annotated strings that was just all of those different versions of the string that you wanted to render, and you could create that sequence pretty easily. And then you throw an animated int on this and a linear easing, and maybe you're done. The code for this is very simple. Set up some before and after annotated string. We kind of hide some of the details of building that sequence just because it's a lot of code that I just described, but then you animate this int either as the first index in your sequence or the last index of your sequence. You give it a little animated spec where you want a 35 millisecond difference for each character and some linear easing, and then you just render this. Like, and it's kind of that simple. If you look on the top left, we can kind of see what this looks like, and it's just something simple like that, right? See it kind of backwards. Okay, that's cool. That's a start. We didn't have shared transition layout in Compose multi-platform last year, so like this is kind of what I did. But now we have shared transition layout in Compose multi-platform, so we maybe need a diffing algorithm, right? We want some way to dynamically say, what is the difference between these two strings? Well, the most common that you'll find is Myers diff. This was published in 1986 by Eugene Myers. It helps you find the shortest edit script for transforming one string into another. We could maybe take each of these edits, whether it be like matching text, adding text, or removing text, and convert that into some shared element modifier as needed. And then we could just maybe lay out all of those elements as text elements that are in a column of rows, right? Kind of redo text ourselves manually. The compose code for this looks rather simple as well, as long as we kind of ignore the details of what this edit script computation looks like. We can set up our shared transition layout, animate content, throw it in some column and rows, ignoring how new lines work for a little bit because those are a little weird. And then our edit function here, or our edit composable, just says, well, if it's a match, we need to do a shared element, giving the key that we get from the match code as well. And if it's anything else, we need to animate enter or exit. Because if it's deleted, we'll animate it out, and if it's an add, we'll animate it in. Now we can decide whether or not we actually want to show this, depending on if we're showing the after text or the before text. If it's a match, we always do it, and then we just need to align by baseline, and that's kind of about it for the structure of the code. Most of the details here was in that computation of the edit script. And if we look at what this looks like as an animation, we get something that maybe doesn't exactly match what we would want. It's not wrong, but it's not great. So what's going on here? What's wrong with Myers, right? Well, so the way Myers diff works is if you place the before text along one axis and you place the after text along another axis, you can create this grid. And you can put a diagonal every time the elements of those sequences match. And then it's just a simple pathfinding solution. You just have to go from the top left corner to the bottom right corner. And once you find your optimal path to get there, you can just follow this path. And if you move right, it's a delete. If you move down, it's an add. And if you move diagonally, it's a code match or character match. Once we've followed this path all the way to the bottom right corner, we now have our edit script. This is exactly what Myers gave us that gave us that animation. He gave us all of the individual characters that got added and removed. That's not helpful though, right? But see, Myers didn't actually really care about strings. He cared about sequences. He cared about sequences of elements. There was nothing really specific about that example that I showed you that said it has to be text. It just has to be a list of some element across the top and a list of the same kind of element down the left. And as long as you can compare them for equality, you can solve Myers on basically anything and get a delta for it. So if we break this down from characters and instead maybe do words, where we take maybe keywords, identifiers, or something like that, we pre-break down the annotated string, not into characters, but into some other kind of thing, we can get a much better diff from Myers that shows, hey, let's remove Kotlin conf and add droidcon. And if we see that animation, we do get something a lot better. Woo. But that's not it, right? We have to stress test this. And so let's look at another after example, where we extract hello into a local variable. This is something that we as developers do all the time in our IDE. We extract local variables from our expressions and we want to put them in a variable, and this is something that we might want to show in slides. This is fairly common. And Myers doesn't handle this super well. Hello kind of disappears and then kind of gets re-added. And the reason for this is because hello is getting deleted and then added again before the print line. So Myers can't track movement of elements. It can only really say it's been added or deleted or it matches. So maybe we need some other kind of diffing algorithm. Another really popular diff algorithm that you might find in Git is called patience. The earliest reference I can find to this is in 2008, attributed to Bram Cohen. You might know him from BitTorrent. And it's named after the patience sort algorithm, which is also then named after the patience card game, also known as solitaire in the US. The interesting thing that it does first as a step is finds all unique elements that are shared between both sequences. And then it breaks this down and finds the longest common subsequence of all of those unique elements in both sequences. Okay, that's a lot of words, fairly complicated, so let's try to break this down even further. If we imagine the elements in the first sequence ordered as playing cards, and then we reorder those playing cards as the unique elements appear in the after list, we might end up with a lot of movement between these two things that kind of show where all of the different unique elements are. We want to find the longest common subsequence here because we want to find a sequence of shared elements where the lines never cross each other so that we can recursively break this down. And to do that, we're going to use something from patience, which is the longest increasing subsequence. All right, how does this work? Well, we take our after list, and we're going to start taking cards off our queue, and we're going to place the 9 in the first stack, and then we're going to look at the next card, 4, and it's less than 9, so we're going to put it in the same stack. Now, 6 is greater than 4, so it needs to go in the second stack, and we draw a line from 6 to 4 as kind of a back reference to the previous stack at its top card. If we continue to do this process, where we keep adding cards below the either creating a new stack if it's greater than everything, or adding it to a stack where it's less than the value, we can create all of these back references and place all of these cards in their stack. And when we get to the end here, we can look at the last stack, and we can follow its back reference all the way to the first stack. And we'll notice that all of the cards in that line are increasing. 4, 6, 7, 10, Jack, King. And we know from when we sorted all of the unique elements at the beginning from the before, it was always increasing. It was from ace to king. So as we kind of take this back and match it up to our original list, we can see that none of these lines cross anymore. So then Patience uses this to kind of break down that diff. He says these elements are always matched, these always shared between before and after, and we'll just take each of those sections that it creates and we'll recurse. We'll do this again. And if we can't find unique elements, he'll fall back to Myers as the diff, which unfortunately is a problem, right? Because Myers gave us an edit script, and that was kind of the core problem. But this whole idea of shared unique elements gave me some ideas. And so I kind of created, it's not really a diff algorithm, but it's like something maybe a little new. Probably not. Somebody's probably done this before. There's nothing new in programming. But we can take all of these unique matches that are in both sequences, and we can maybe expand the ranges, right? If we find the main keyword that's in both functions that both have parentheses afterwards. So we can expand those matches to consume as much code as we can. And then if we recurse doing this again, where we take all of the elements that were unmatched and try to find matches again and expand again, maybe we can consume and create this whole diff. Code for this looks fairly simple as well, very similar to Myers. We'll kind of hide the complexity of the matching code, but it is just, again, kind of thrown in a remember here, and the compose code is very simple. It's a shared transition layout, animated content, column of rows of text, right? Here we're kind of handling new line explicitly. But then if the piece doesn't come with a key, we know it's never been matched, so it needs to get either animated in or out. We can also do something fun here with annotated strings, where if the text of the annotated string matches, but the style doesn't, we can kind of crossfade, so we'll do a shared bounds. And then if it does match and the style matches, we'll do a shared element. And then you just throw this in a text element with that modifier and align it by baseline, and you get a much better animation where hello now does follow into the greeting local variable. Let's see it one more time. Now, there's a fun little inconsistency here, though, which is sometimes the quote that comes before hello follows hello, and sometimes it follows the print line. And this has to do with the order in which I'm expanding the ranges. So when it follows hello, I've expanded hello first, and when it follows print line, I've expanded print line first. So yeah, there are definitely some problems here. There's some visual inconsistencies, and this is unfortunately a problem with giving a very meta talk about a tool that you use for your talks. You can't really fix the tool because you're so time crunched to give your talk. But I do have ideas now, having gone through patience in more detail. Maybe we can use that longest common subsequence, expand those elements first because we know they'll be stable across both elements or both sequences. So there's definitely some ideas here. And just to show you that like none of this is canned, I have 2 literal text fields, if I can find my mouse, here in my slides. So what if we changed, oh, this is weird to do. So I can like animate before to after, and I can replace the text here to something that, yeah, I did copy and paste. But now we can pull out both hello and droidcon. There's another fun example here of maybe now we move both of those to local variables as well, and so you can kind of see the names floating into the parameters list there. But you can kind of create some really cool animations with this. This was an animation that I created for my recent talk at KotlinConf, where I'm kind of showing what power assert does, pulling out all of the local variables. This is actually what made me go down this whole route because Myers couldn't handle this, and so I kind of had to redo it all for the KotlinConf talk. And then one of my favorite parts of the animation is kind of coming up when it collapses everything back down together to kind of restart the animation right there. Kind of cool how it tracks everything. And then there's a really fun compose equivalent to this as well, where it kind of shows what the compiler plugin is doing, adding all of the different parameters that compose does, surrounding all of the things with the groups, making it skippable, and then adding the restart there as well. So yeah, Magic Text is pretty cool. Obviously, there's a bunch of work that still needs to be done that I'm hopefully getting to here after DroidCon, that when I have time again. But if you want to see storyboard in action, I've been told that Jesse's doing, I've been told that Jesse's doing one slide with storyboard, and Alex is apparently doing his entire talk with storyboard. So if you want to kind of see something similar style as well. But then I guess in summary for this entire talk that was disguised as a composed talk, you should definitely write a diff algorithm. It's a lot of fun, and you'll definitely learn something. And maybe if you write a better diffing algorithm than what I've done, I can use your diffing algorithm, and then I'll be happy about that as well. So, all right, thanks everybody.